Thus x double dash is the variable 0 to x double dash equals xc, right? So let us do the magnetic carrier concentration. For the base we have already determined. Let's take the thermal equilibrium electron concentration in the base region. This is our NB0, okay, and at the base, as the base emitter, let me write, this is your emitter, this is your base and collector, okay, N P N, right? Forward active mode, so base emitter region is forward bias, so you got this as the maximum concentration that we have obtained. NB0 equals NB at x equals to 0, right? I can write that way. NB at x equals 0, or NB equals NB0 is thermal equilibrium concentration, e to the power EVV base emitter voltage divided by KT. Okay, the concentration maximum, and this base collector region is reverse bias, so the concentration will be 0 here. So you can show it like varying like this, okay, and reaching to this point. Okay, this is what we said. Now the emitter base region, so you got the maximum value somewhere, right? Holes coming from base to the emitter region, so that gives us the value. We can write this as P in the emitter region at x dash equals 0, okay, which is maximum here, that is given by PE 0, that's the thermal equilibrium concentration of holes in the emitter region. These are the magnetic carrier concentration, e to the power, the same way we can write EVBE over KT, okay, write this. So from here to the thermal equilibrium concentration is, let's say this is your PE0, so it will vary from here to this PE0. Okay, now come to the collector region, the thermal equilibrium concentration. Let's say this is P, this is the N region, so holes are the magnetic carrier. So this is your PC0. This is a base collector region, reverse bias, so it will vary from 0 to this PC0, like this, okay. Yeah, concentration is 0 at the edge of the base collector. Okay, so this is what we have already done, right? The direction of the electric field, if you see here, the electric field direction, this is the direction of the electric field, and here this is the direction of the electric field. Okay, so this is overall thing. Now the same way like we did for base region and the emitter region, exact the same way we will start for the collector region, and we need to start with the steady state excess carrier concentration in the collector region. Okay, so for that we need to write that equation. Okay, if you remember the steady state excess magnetic carrier electron concentration equation, okay, revisit that concept. If you have forgotten that, then we will start with the collector region. So in the collector region, if you write the equation, you can write d square 20x square of delta PC x double dash minus delta PC, these are the excess carrier, okay, over LC square, the diffusion length, you remember, in the collector region equals 0. We'll start with this. What is this LC square? Can be written as the diffusion coefficient and then the relaxation time at also 0. Right, so this is it, and the excess carrier concentration can be written as the emitter region, can be written as the non-equilibrium pole concentration minus the thermal equilibrium pole concentration in the P region or the collector region. Okay, let's write the general solution for it. The general solution for this above differential equation we can write, so delta Pc function of x double dash can be written as some random constant g exponential e to the power x double dash over LC plus another random constant h exponential e to the power minus x double dash LC. This is the general solution for this differential equation, right? So now if you use the boundary condition delta Pc at x double dash equals 0, if you substitute x double dash is 0 here and here, right, then you got e to the power 0, e to the power 0, so that gives us g plus h. Okay, now if you use the other boundary condition, that is delta Pc, the value of the neutral collector width is x double dash equals xc, right? Here if I'll substitute, I got g, then exponential for x double dash we are substituting xc over LC plus h x e to the power minus xc over LC, right? Substituting. Now what we are using here, one assumption, that is the collector is long enough. Okay, so for that assumption we'll consider the collector, okay, is long enough, okay, so that the neutral width of the collector region, right? Okay, so that mathematically if I am considering this to be infinite, then what will happen here, the second term minus infinite, if you will substitute, then that term will be 0, right? So we can write that the second term in the awake equation, the second term becomes 0. Okay, so this term vanishes now, right? So the remaining we can write, so we can write delta Pc x double dash, okay, is 0, delta Pc x double dash 0 is your what, original concentration, which is Pc, okay, x double dash is 0, right, the non-equilibrium concentration at x equals 0, and then Pc 0, right? So the concentration at x double dash 0, non-equilibrium concentration, you can see it is 0 here, so I will substitute that. Okay, so if I substitute that, I got 0, and then the value thermal equilibrium is Pc 0 as it is, so we got this value as minus Pc 0, right? So minus Pc 0 we got for delta Pc x double dash 0 equals minus Pc 0, right? So delta Pc, now when x double dash equals xc, right, then also we can write Pc x double dash equals xc, we are substituting minus Pc 0, the thermal equilibrium value. So what we got here, Pc at x double dash equals xc, Pc at x double dash equals xc equals Pc 0 equals Pc 0 minus Pc 0, that gives us 0. Okay, now this is what we got, fine. So here you got delta PC at x double dash 0 is minus PC 0 and delta PC at x double dash equals xc is 0. Right, now go back to the solution, right? So here what you got, g, this term is 0, right? Then we can write delta PC at x double dash xc here is equal to g exponential of xc by lc, right? And again we got this to be 0, we can equate that, so we can write this g, okay, exponential e to the power xc divided by lc equals 0. That clearly, that means this is your g equals 0, right? So g equals 0 you got, so you got g equals 0. Then if you substitute for here, you can see this g plus h. Now this one delta pc at x dash equals 0 is g plus h, and that is equal to your minus pc 0, right? So we can write that, so substitute g plus h equals minus pc 0, right? This implies g is 0, so h equals minus pc 0. Let us rewrite our equation, general equation. So our general equation, delta pc x double dash equals, what do you got, minus pc 0, that's for h, right? G is 0 already, so this term will not be there. For h we can write, okay, so with the minus xc by lc, so that we will write delta pc x dash is equal to minus pc 0, and we got this as minus x double dash over lc. Okay, so this is what we got for the excess carrier concentration, minority carrier concentration in the collector region. Okay, thank you.